Hi, everybody. My name is Alexander Zdorovets. I am senior developer in MTS, and today I'm going to talk about transformer language models for ASR. Well, it's not a very difficult subject, or maybe not. Well, I would identify four bullet points: transformer language models, ASR, and which is four also is very important. Let's move on. ASR, what is ASR? Well, I first heard it, I didn't know what it meant. It's automatic speech recognition. So you can schematically view it as this. We have certain raw audio waves, which go raw signal, which goes to black box, which makes the main processing. And then we have a text, graphic text. It's a graphic speech. Why we need it is because speech and statements and the language can be either audio signal, and text or graphic form. Interestingly, if we put the arrows the other ways, then the text goes the text to speech. But I am not going to talk about that. Well, I did it too, but it looks very different. So if we zoom to our black box, we will see three components: acoustic model, it's a decoder, it's language model, and decoder. Well, acoustic model, well, it is processed. It uses the language of the knowledge of the language model, and to predict a good phrase. Well, more formally, but not graphically, well, which looks beautiful but not that useful, we will see fundamental equation of statistical speech recognition, fundamental equation, where you can see all the graphs, and W at the beginning is the text. We would like to maximize the probability of the text from a vocabulary using our raw signal, and you can see it's A here, and you can see arrows, and we can put it into the equation to the right, and all our components are all well seen here. And as is known, everybody has different hypotheses of consistency of words, and the same A, well, but we can ignore the denominator. Acoustic model, well, it's this one model. Well, we can use different models. It's a Gaussian mixture model, hidden Markov model, and DNN, like CNN, well, loves it. Those, well, the acoustic models are based on phonemes, and that's the problem. That's what I'm going to talk about. Mostly it's phonemes, which is quite a difficult thing, and as I can show, if acoustic model, well, I didn't work with it, but there's a window which goes along our spectrogram to extract some features from it, predicting, again, as far as I know, either a phoneme or a special symbol, and then it collapses. All similar phonemes collapse between those signs. Language model, as I said, acoustic model is low level. It's phoneme. It uses phonemes, which is the lowest level of the language. And if we want to produce something very useful, then we will not, well, just phonemes will not be sufficient, because it doesn't know much about the language, and enriching it with the knowledge about the language provides you a huge boost for your efficiency of recognition. And you can see one of the options of the model at this picture, and you can use very different things. It's n-gram models, for instance, or and also transformers or RNN and transformers. But formally speaking, the formula of the language model is provided here at the bottom. And please, well, roughly speaking, we will need it. And roughly speaking, the probability of, well, the language model provides probability of certain sentences and text, and actually it assesses the probability of separate words and predicts the token or probability of the word depending on the previous one, or either all of them or the text. But that doesn't matter much. And the third component, that black box, a decoder, the decoder, which glues both the audio and language model. And as far as I can judge, there are two big options here. Well, it's not in the architecture, but I will talk about that now. Or maybe we can add the language model. Is the first pass or the second pass? The first pass is that we right away adding LM scores to audio models during decoding. So it's or the audio model tries to decode, and we right away add some the knowledge from the language model, or merging some hidden states or prefix search and so on. There are a lot of options there. And the second pass, and you can call it also rescoring, it works as follows. We have an audio model, provides some hypothesis, what it heard before, and we asked it to verify the norms of the language. This rescoring example is here because I was doing it. So here are some predictions from my head. And audio model provided the model what it heard, the most probable and the least probable answers. Then the model configurates or calculates the number or the set of words. Based on the LM perplexity, we can rearrange. Which and this differs sometimes, this list or the order of audio and language models. And then we can just ignore the audio model and take only the predictions of the language model then to match it. But there are different options to do that. There are very different options. Now let's get over to the next subject, because I will try to do it beautiful, but transformers, but not the ones, but those who came in 2018 and replaced the NLPs completely thanks to Google. And transformers consist of two things, coder and decoders, and I'm sure you know. And just to remind you that the decoder which codes a certain consistency, and there are some decoders that are trying to decode what is coded. What was coded, and I'm using interestingly that you can use them separately. Google did it in 2018. They published their open AI team also in 2018. What they did, it was the decoder. This is briefly for you to understand how it all operates. So here is the explanation that I like very much.
So the tokens are in circles. We embed them into three vectors: query, key, and value. And each query looks at each key. So first query, first arrow, and we try to catch, to have a score, to have a measure of similarity. There are various approaches, but that's important. And then we can use this max to have a ratio, a coefficient from 0 to 1 to have the value of the vector, of the value vector. And then we use linear changes for further calculations. What is the idea of such approach? What is the efficiency and benefit of it? For each token, we have contextual value, the value which is impacted by the context and which is coded, which is coding the information in full in this particular position for this token in this context. Let's get back to BER2 and GPT and the language model and the equation of the language model I showed a couple of slides before. For the probability of the text is and is all token probability of all tokens taken together. And what picture is the most like BER and GPT to the right? So the right part, the right picture is the most suitable since GPT is a transformer decoder and that's how it works. The main difference, what is it? The main difference is that encoder is looking to the left and to the right. We have token, it looks to the left and to the right. And this is bidirectional encoding. And yes, sometimes it is more full, but it is more comprehensive, but in general, yes, there are some peculiarities to it. And the decoder is looking to the left only because it is generating the new text. It cannot look forward because in generation, if looking forward, there is nothing. That's why on this picture, we see why me and my team, why we use GPT for our models, because it suits us best as a language model. And we need to say that the BER can also use for language models and the raw research and articles on this, but it is just some heuristics. But to use GPT is more logical. And then let's move forward. We have a task to understand the speech, and we have knowledge, we have transformer. We use GPT-2 because it is a more logical thing than BER, and better than we use a decoder. And here, yes, we can also discuss it in more details, but let's just move down the slides. And I want to give you an example at the end how we use it. This is real figures. We have understanding of speech, and now it works on n-gram. I don't remember what team is working with it, but I tried to make a solution that can compete or be better. An R&D thing, sort of. And here we show two experiments. First is at the top. We have two acoustic models. Yes, models can be trained in various ways. So two acoustic models here, and we need to select, and each is promoting one hypothesis. We have two, we need to select one that is better than the other, the best hypothesis. And we have two n-gram model, number 1 and number 2, and we have GPT-2. We select and we calculate the border rate and the rate and the deviation from references, the real sentence that was articulated by a user. And here we see that in this experiment, GPT-2 is better than n-gram model, but again, not very much better. Yes, obviously, every 1% is better from 1 to 0. This is the scale here. Every next percentage is good. Another experiment, two models, 2 n-gram, 2 ODL models and n-gram, 2 of them, and GPT-2. And in each acoustic models, we have 20 decoders. And GPT is not very good here. An n-gram model became even better than before. But I should say that this is old figures. Now we have new cases. I haven't yet processed them, but it should look better. So I am approaching finishing slides of my presentation. We're pressed of time. I just want to say that we had this as an overview presentation. I hope it was interesting for you. If you want something deeper, I of course I couldn't tell you everything in these 15 or 20 minutes. I just want to give you references for more sophisticated materials. So here in the page of GitHub, SYHW, where are we? So where guys or one person is collecting the top solutions in ASR. Here we see the third column in this table is the links to the articles and the stack they use, and to the left is the results of such approach. So cool thing, very useful to see what new things are emerging and what other interesting things can be developed. I hope you have the link now and you can use it. So that's it from me. Thank you very much for your attention. Alexander, thank you very much for your presentation. A short question. Am I right saying that GPT is used in production? Or I'm wrong. If it is used in production, then in what size and what problems you faced when using it in case calls to operations? Thank you for your question. Not yet in production. This is an R&D thing now. It's more about proof of concept because now in production we're using more reliable solutions. But we use the medium model. I don't think we should use something large because usually the queries of users in audio format are not very long, and it doesn't take too much to process them. But it's 1.5 gigabytes, and inference it is not slow, but it is not fast, I'd say so. Well, 50 requests are processed in half a second. But it was just a rough estimation. It doesn't make sense to optimize now. Before we have good results, then we can go into optimization and better efficiency. But I think it should be good. I think it'll be efficient. Thank you very much for your presentation, Alexander. Thank you.